So my background is I did my undergraduate in electrical engineering and computer science at MIT. Then I did my PhD in physics at Cambridge, which is where I first met Mike Hobson a long time ago. And after a postdoctoral fellowship at the University of Toronto, I spent 5 or 6 years as faculty at Harvard University in the School of Engineering and Applied Sciences there. Um, I One of the things that happened while I was at Harvard is I founded a startup and that spun out of the research in my lab, and ultimately we had a successful exit and sold that startup to Twitter in 2015. I spent a couple of years at Twitter and then at Google in industry before deciding I wanted to return to academia, where I have a little more intellectual freedom. And I joined the faculty here in Princeton then in about 2017. So my research is on a lot of different things. I like to think a lot about methods in machine learning, AI, computational statistics, and I also like to think a lot about applications across a broad variety of areas in science and engineering and beyond. I would say a unifying theme for a lot of my research, and that is the thing that kind of relates most directly to quant insight, is I really like to think a lot about how we can quantify uncertainty and complicated and noisy systems, and how we can reason about unobserved structure in these systems. And what I mean by that is that we see complicated dynamics around us all the time. Obviously, financial markets contain many different kinds of actors, many people behaving different ways, different ways we can measure activity across many different kinds of assets. And we imagine, though, that beneath that there's interesting latent structure. And this occurs not just here, but it is also a way to reason about astronomy, say, or a way to reason about neuroscience. We imagine there's activity in the brain. This activity in the brain can be connected down to, and can be sort of reasoned about in unobserved structure that we think is the signal maybe that's being represented there. Or we see some signal from a remote object in the sky. We can think about the physics that must be sitting beneath that. So when I say latent structure, that's what I'm talking about. And when we talk about uncertainty, then, because we can't see that latent structure directly, it's not enough to simply sort of make one hypothesis about what it is. Instead, what we like to do is reason about a distribution over hypotheses. We recognize the fact that we have imperfect knowledge, not just due to the fact that this information is hidden from us, but also that the observations we do get are noisy. And so by combining, and it turns out that by combining representations of uncertainty with reasoning about latent structure, that we can make more optimal decisions that take into account all the possible ways that the stuff that we see, like how it might have come into being. And on the side of financial markets, this is of course very important, because we do think that there is understandable, interpretable structure beneath the dynamics of markets, and that we can make decisions that account for that structure, but also account for the fact that we have imperfect knowledge of it.